Hello everyone, this is Ayush Gupta and today I am going to be presenting our work You Can Run But Not Hide, Improving Gait Recognition with Intrinsic Occlusion Type Awareness. So, what is gait recognition? Gait refers to the way of walking of a human and it consists of various different parameters. These parameters can be measured with very precisely using wearable sensors, and this is what they do in medical applications. But for the field of biometrics, to recognize people, we usually have vision based gait recognition approaches because they can potentially be used from videos captured at very long ranges. And when face and body are not available, Gait can be used to exploit temporal information to identify the subject better. So yeah, these are the kind of data sets we have. We work on outdoor in the wild scenarios, and for that two data sets exists. One of them is GREW, which is a publicly available silhouette based data set, and another is BRIAR, which is a much larger data set focused on biometrics from long ranges and turbulent data. Generally, gait recognition is done using silhouettes, but recent works have started exploiting RGB as well. So current gait methods follow kind of similar structure where they obtain a 3D representation of the input video through a sequence of 2D or 3D CNNs. They horizontally split this 3D representation into multiple parts. So the top part might have features corresponding to the head, the bottom part might have features corresponding to the legs, and then they somehow combine these representations in an aggregation step. The differences between current methods arise in how they compute these 3D representations, where do they do this splitting, or how do they aggregate these features. But they all have this common structure, and that is why they all suffer from this one vulnerability, which is occlusion. So because the current approaches split the input into horizontal parts, and there is some inherent expectation about what each part contains, if there is occlusion, one or more of these part features will get corrupted. And because the aggregation steps gives equal weightage to all of these parts, the entire gate signature might get corrupted. And this is what we want to target explicitly when we work with occlusion. So our idea is that if the network knows where occlusions are present, what kind of occlusions are present, in one sense the network is occlusion aware, it will implicitly learn to give less weightage to these occluded bad regions. And we do this through the addition of an auxiliary network which tries to identify the occluded regions in the input. And the guidance from this auxiliary network subsequently makes the gait recognition method or backbone occlusion aware. So the occlusion detector is the auxiliary network I talked about, and it's trained to classify the input into multiple occlusion classes. It's trained separately from the gait recognition backbone, and when in the next step when it's used to guide the backbone, its weights are frozen. And obviously the classification head is also discarded. We just use the intermediate features beta for the occlusion detector. And during inference, when it's being used to guide the backbone, it can be used in two different modes. The transient mode gives different features for occlusion features for every frame, and the cumulative mode gives a single feature for every for the entire video. These modes will become more relevant later on when I talk about them. So this is the overview of our gait recognition pipeline. We obviously train the occlusion detector as a pre-training step. Then we extract silhouettes from the RGB video, we perform centering, cropping, and then we also apply synthetic occlusions. Now, this synthetically occluded video is sent both to the gait recognition backbone and the occlusion detector. One of the intermediate features of the backbone, let's say X, is taken and it's combined with the occlusion features beta in the occlusion awareness module, which outputs occlusion aware version of X, say X prime. When we insert X prime back into the backbone, the subsequent layers of the backbone and finally the gate signature also becomes occlusion aware. Occlusion awareness is visualized here by the color purple. So yeah, occlusion awareness module M inserts occlusion awareness into the backbone. And yeah, this approach is model agnostic, as in we don't make any assumptions about the architecture of the backbone, so it can be used with any network, and the training procedure of the backbone stays unchanged. So whatever original settings have been designed for the backbone, we use the same settings. Anyway, we are not training the occlusion detector. So what does the occlusion awareness module do? Its aim is to combine the intermediate features of the backbone with occlusion aware features beta. And this is where the transient and cumulative mode of the occlusion detector come into play. So what we do is, for our experiments, we pick two positions within the backbone. And one of them is from the earlier layers, one of them is in the later layers, and then we perform several kinds of computations, several methods of combining x and beta. So if x is chosen from position 1, the earlier one, there is still temporal information present in those features, and to perform the computations like adding and concatenating, passing them through a 3D convolution, the shapes of x and beta must be compatible, and that is why we are using the transient mode here, because transient mode retains temporal information. If you pick position 2, temporal information is not present in the backbone, in the features, so we use the cumulative mode of the occlusion detector. And yeah, these are the different kinds of methods we try. For position 2, yeah, we try concatenating them and passing them through fully connected layers as well. So yeah, this is what the occlusion awareness module does. And yeah, there are not much works currently focusing on occluded gait recognition, so we come up with our own two baselines. Baseline 1 is a network trained on complete videos and evaluated on synthetic occlusions without any occlusion awareness, and this answers the question, how good would the original model work on occlusions. Baseline 2 is the same network which is trained on synthetic occlusions. It's basically the simplest thing we can do to adapt the network to occluded data. And yeah, these are the results for GREW dataset. Due to random applications of occlusion, the results vary slightly each time, and we report the mean and standard deviation over 10 evaluation runs. However, the trend is clear. Inserting occlusion awareness helps across different backbones. These are the same results for the BRIAR dataset. Here also we can see this trend. So occlusion awareness helps across backbones. And yeah, these are the results for the different kinds of occlusion awareness methods we tried. And we see the complex deferred concat, the method where we concatenate x and beta and pass them through fully connected layers. It performs the best. So another experiment we want to perform is we want to see whether our method is able to generalize to unseen occlusions. So far all experiments were done on similar kind of predefined occlusions, and here in this experiment we come up with two new types of occlusion, one of them being dynamic occlusions, where yeah, the occlusion can change with every frame, and another is real occlusions present in the BRIAR dataset, where tall grass occludes the bottom part of the subject from view. And here also we see that the occlusion awareness model is able to generalize better than the baseline to these unseen occlusions, and we think it's because even though occlusion detector is not trained on these occlusions, the intermediate features beta still have some relevant information which the model is able to exploit. Another thing, if you're working with dynamic occlusions, one thing which comes to mind immediately is why not use the transient mode of the occlusion detector, because it gives different occlusion features for every frame. And this is what we do exactly in this experiment. We train two different networks with different occlusion awareness methods, one of them using the transient mode and one of them using the cumulative mode of the occlusion detector. But counterintuitively so, we observe that the one with the cumulative mode, namely deferred concat method, still performs better, and we conclude that occlusion awareness is more helpful in the deeper layers of the network. So yeah, so that's all for our work. For future work to improve this, we could try introducing concrete architectural changes in the backbone. This might lose the model agnosticity of the approach, but it also might boost performance on occlusions. Then we also currently we evaluate the approach only on synthetic occlusions because of lack of real occluded data. That yeah, if such data is present, we should verify this approach on real occlusions as well. Thirdly, yeah, we currently work with silhouette data, but recent works have shown that RGB modality can also boost performance. It's not so trivial to simulate real looking occlusions on RGB data. Obviously, you could use generative AI to do that, but yeah, this is something which we leave for future work. These are the references, and yeah, thank you.